In this video, I'm going to be going through the 2020 trial examination. So first of all, we're going to go through the 20 multiple choice. The first question is identify the control surface located at F. So we have lots of letters around this picture, but F points to this flight surface on the outer end of the wing. Now, a lot of people said flaps. I think that I haven't looked at the data, but a lot of people look like they said flaps. The answer is ailerons. Okay, the next question, I think there's a typo here, and I'm trying to keep a track of typos, but which of the following stress-strain curves best represents a brittle material? So ductility is represented by the length of the stress-strain curve. So brittle is the opposite, or could be thought of as the opposite of ductility. So the shortest in terms of length in the x-axis is B, so B is the answer there. Okay, the next question is a Pascal's principle question. Now, the big thing you've got to look at here is, are they giving areas or diameters? I tell you, I did this question wrong when I went through, when I was like self-checking, until I went back and thought, wait, no, I need to make sure it's area and not diameter, right? I often show questions that focus on diameter. In this case, the answer was given as area, right? So the area of 25 versus 100. So what is the area ratio? 4 to 1, 1 to 4. So that means that whatever our force is, we're going to get a mechanical advantage of 4. Now, you'll notice here that I didn't say assuming 100% efficiency, right? If it doesn't say assume 100% efficiency, there's no other way that you could work it out. You could probably say, if it was a handwritten question, you could add assuming this ratio of efficiency, but in this case it's a multiple choice. You couldn't have used any other value and got an answer that worked. So which would be plausible. So that's C. Okay, 30 multiplied by 4. Okay, which form of modulation is the best for long-range emergency broadcasts? Okay, you all have the answer in front of you. So the answer is amplitude modulation. Now, bit tricky. Phase and digital, they're the same thing. Tricky, tricky, tricky. The advantage of AM is that because it has a very long wavelength, it can go a long way. Now, the downside of a very long wavelength is that it doesn't have a lot of data that can transmit. I was watching a YouTube video recently about submarines. I think I posted it on the 5G guy with the tinfoil hat. And submarines, they can receive messages underwater. They have to have incredibly long wave frequency, so really, really long wavelength frequencies. And that means that they can only send, I think, about a page of text a minute, or something really small amount of information that they can send, right? So I think it's something like a character every half a second. Yeah, 2 characters. Might be 4 characters a second. Anyway, the point is it's very, very low frequency compared to what we can send ordinarily. And that's so that it can go a long way or through a very dense medium. Okay, question 5. Which of the following best describes doping of semiconductors? I took this from the recent trial. I thought it was a reasonable question. The answer is A, so we'll move on. I just want to go through the other ones. The addition of other atoms to increase the number of grain boundaries. Well, that's more like an interstitial alloy. The addition of electronic components such as diodes. Well, that's just the field of electronics, right? That's not the case of alloys. The addition of high conductive materials such as copper. Well, so we add copper into brake pads for its heat conductivity. But the answer is the changing the number of positive and negative charges in a material. Now, when I read that question, I'm like, oh, that sounds good. I don't know if it's right, but it sounds good. It's definitely on the list of options. The other options here are all bad, though, right? So they're all wrong. Now, I would say, if you ask me to describe doping, I would say doping is, in the case of semiconductors, usually we're talking about silicon, and I'd say the inclusion of similar but slightly different elements such as phosphorus or arsenic or boron, which either have one additional proton and electron or one fewer proton and electron, right? Their atomic number is either one higher or one lower. Well, actually, not entirely, but anyway, maybe this is the better answer. Now, in terms of the Veritasium guy, he talks about increasing the number of electrons or increasing the number of holes. So actually what it is something that has one more valence electron. But remember that it doesn't actually increase the negative or positive charge, because we're adding a whole element. We're not adding ions or anything. So the same number of protons and neutrons goes up. I probably just, what I've said there has probably confused more people than it's helped. But remember that Veritasium video is there. There's also another video with the scary looking silicon atoms. They're both quite good. Okay, which of the following best represents a rectified current? I don't have the stats. I'd be interested to see how many people got this right. I thought this was... I sort of made this question from a bit of a HSC question, and I thought that it was a pretty reasonable one. Who got this one right? Most people. There we go. Either it was too easy or I've just taught this really well. Okay, so the answer is D, because we're just shaving off the bottom. Now, we could say, theoretically, you could say that this was a rectified current, right? This A could have been a rectified current. So if I was writing this question now, and I only wrote this a couple of days ago, I would have said which best represents a half-wave rectified current, or this one here would be a smooth rectified current. How do we smooth the current? This question will come back later. Starts with a C. Capacitors, right? Now, but even then, with capacitors, we still have a bit of a sawtooth, right? We still have a bit of a zigzag pattern. Okay. Okay, which of the following material testing methods is used to determine the toughness of metal alloy? Well, if we go to our testing page, right, on Facebook, we don't want that. That was wrong. Okay, so what we're going to is a picture of Sam Rockwell, even though he didn't answer my question on Reddit. There we go. Okay, so here we have our two toughness tests, right? We've got iZod, right? General Zod listening to the iPod. He stands up and faces Superman. And here we have Sharpie, the French guy, lying down crying. Yep. Okay, continuing. iZod and Sharpie is the answer for that test, right? Pineapple song reference. Okay. Composites are widely used on structural components of aircraft, boats, and racing cars. Of the factors listed, which is the main reason for their use in these applications? Okay, so D is the only one that is actually applicable, right? So this is something where I could have said things like corrosion resistance, right? And corrosion resistance is a reason why they're used in planes, but the main reason we use them in planes and racing and boats is because we want lightweight, right? So that's the answer there. D is high strength to mass ratio. Okay, question 9. You guys walked out of the exam, and I knew there'd be something that you'd complain about. And I think as far as things go, the fact I didn't get called over to the exam is probably a good thing. Okay, so here we've kind of got 2-for-1 questions. So, what is the likely carbon content for steel used in structural members in residential construction? Can anyone tell me that answer? Okay, I thought... 0.3, I'm so pleased... No, 0.3. 0.3. Yeah. I took that question out because I thought that was too easy. But, okay, 0.3. Yeah, thanks. Okay, but I thought... I was also looking for a question with some room to put in... I want to have a resistance question. So, okay, how does this work? Well, these two resistors in parallel, what we do is we add the inverse of their resistance together. So what's 1/6 as a percentage? Or a decimal? 0.166 repeater, right? What's 1/4 as a decimal? Okay, add those together, what do you get? 0.41 something, yeah, 0.416666 repeater. Okay, so what is the inverse of, so if you take 1 divided by 0.416, okay, 1 divided by 0.41666 equals 2.4. That is the resistance of those two. Now, as a rule, it's probably somewhere a little bit less than the average of the two of them, right? So half, or a little bit less than, yeah, half the average. Yeah, half the average is just as, I'm not saying it's right, but I'm saying that's a rule of thumb, right? And that happens to be right. Then we add the next one in series, so we add 3 to that number. 3 plus 2.4 gives us 5.4. So the answer is C.
How do you do the resistance of the two in parallel?
1/6 plus 1/4 is what?
It's like 5/12 or 0.42.
Yeah, okay. Then 1 divided by that number. I just did it on the calculator here.
Yeah.
2.4? Yeah, and then add the 3.
I didn't realize
Hey, it's okay. That's why we have a trial exam, to prepare us for the HSC in case that comes up. This is a learning opportunity. Use all of these questions as a chance to say, hey, there's plenty to learn here. Okay, this is a pun special. I came up with this question. I wanted to have something that referred to frequencies. I'd seen a question like this somewhere recently, and I thought, oh, that's good that you guys didn't seem to answer this one confidently when we were doing a little bit of revision. The question we looked at was for satellites. What is the frequency that we communicate with satellites? The same as Wi-Fi, same as the microwave, 2.4 gigahertz. It's anything in the gigahertz range, so it can actually be far higher than 2.4 gigahertz, but you know, in that range, right? Wi-Fi is usually 2.4 to 5, yeah, gigahertz. Okay, so C is the answer there. Okay. 11. Which of the following chronologies best represents the order in which telecommunications were first developed? Okay, I tested that question with Year 11 to check that you'd be okay with the chronologies word. When I did a question with Year 11, I didn't specify that it was the order in which they were historically used, and that was the best way I could phrase that sentence. Okay, so Morse is the oldest. Right, that makes sense, because Morse carries less information than the telephone or the telegraph. Now, specifically, the difference of which one came first, the telephone or the radio, look, I'll be honest, I struggle with that one. And that's why I deliberately wrote the question so that that one wasn't something that came up. For the record, we've got that there. This telephone was what year, Kai? What was the telephone? 1876, and I think the radio was after that. 1896. There you go. But they're pretty close. Close enough that would be hard. For, you know, that's really testing some serious knowledge here. I think most people are aware that optical fiber is like 50 years old, whereas Wi-Fi is less than 20 years old. So actually, no, I'm looking at the board at my wall up to the back. It's 1997's Wi-Fi, so it's actually a little bit more than 20 years. Okay. So the answer is Morse has to be first, and Wi-Fi has to be last. That makes B the answer. Yep, we're all good? Yes. Okay, pitot tubes are used for what purpose? Airspeed. Who got that one right? Okay, one person, 2 people. I thought that was easy, right? I haven't looked at the stats. I wish I knew the stats. I thought that was easy, right? Okay. Which of the following is used to prevent stalling? Yep. Slats, right? I've got a picture about that. It was one of my first engineering memes. Do I have that here? Can I find it quickly and easily? Oh, maybe I don't have it here. Maybe it's on this. I have my picture of Michael Slater walking past the slot machines. Anyway, we'll have to find it later. If I haven't shown you that, that's a crime, because that's one of my first, one of my original engineering memes. Okay, so I thought all those distractors were pretty reasonable. Okay, the properties of 0.6 carbon steel can be altered using the following procedure: heating up, then cooling an oil, then reheating. Which one is that? Quench tempering. Now, you could argue that that is also the case for precipitation hardening, right? But it doesn't apply for 0.6 carbon steel, right? Precipitation hardening is for stainless steel, for aluminium, and I actually based this on a question that I'd written previously on precipitation hardening. So the carbon content, the fact that it's 0.6% carbon, is really what tells you what it's going to be. Okay, so the next question. Okay, so I'll also say in the. I was going to mention a question in a different trial, but we're not going to discuss that now. I'm going to give you that trial, and then we'll discuss it when we review it, because I don't want to give you any answers. I'll just point out that it was, I thought, a hard question. So, okay, which of the following shows a bolt threaded in a blind hole to the AS1100 stand? Now we have talked about what is a blind hole. Well, what's the opposite of blind hole? A through hole. Yeah, if you can see through it, it's a through hole. If you can't see through it, it's a blind hole, right? It just means that the hole doesn't draw all the way. Question 15. Okay, which of these represents a bolt threaded into a blind hole? B is the answer. That's right. Okay, so with A, the sectioning has gone into the thread. That shows an empty thread, so that's confused, right? That doesn't work. Here, this is showing a full thread kind of all the way through, right? Like, so this C could theoretically be the answer, right? It's not, but C represents a fully threaded bolt that is fully screwed all the way into the very edge of the hole. So that's not likely to be the case, right? This one here shows us a partially threaded bolt, right, with some gap in the bottom, and that's far more likely. So I think C could be potentially correct, but I like B is the better answer. Okay, this one here, again, doesn't work. It's actually worse than this one, because here you can see that the angle has changed, right? And the angle changing there, that doesn't just make any, that makes the least sense of anything. Okay. Oh, yeah, no, all of the multiple choices are there. Just if you want to grab yours, you might have written notes in them or whatever. Yeah. Okay, sorry, I should have handed those out so you could follow along. Okay, question 16. I should zoom in. Okay, I took this off a recent trial. A mild steel rivet is used, well, I modified a recent trial. A mild steel rivet is used to join two copper sheets to form, there you go, I left out another word, to form a galvanic cell. Where is galvanic corrosion likely to occur? Okay, so let's go to our Facebook pictures. Yeah, Rad Cat is cool. He doesn't worry about rust. He's got a house full of gold. Angry Ox, on the other hand, he's angry because his house is all rusted. Yeah, Rad Cat doesn't rust. Angry Ox, he's angry, right? So by me telling you that steel is the anode, it's indicating that that's where it's going to rust. Now, what's also worth pointing out is that the Angry Ox has low quality oxygen, right? Low oxygen, and is also stressed. Now, the thing is, you could have said, potentially, at the stressed region. Did anyone say at the stressed region? Okay, great. I'm glad no one got that wrong. The stressed region, I wrote that down. The reason why stressed region is not acceptable here is because I specified galvanic corrosion. Yeah, I specified the type of corrosion. Right? Sometimes I have to do that as a question. Okay. Very quickly, I'm going to write this on the board. It doesn't make for great viewing. But I've got pH equals mu, brackets, mg plus or minus PV. Now, in this case, they're giving us 30 degrees. That makes life pretty easy. That's 0.866P equals, what is our mu? 0.4? 0.4. What is our mg? Our weight? 230. Now, do we add or minus? Are we reducing the weight or increasing the weight? Reducing the weight. So it's minus, and PV is 0.5P. Okay, so this number here, can someone tell me what that is? $92. Wait a second. 92? Yeah, okay. Tell me that. Oh, I guess I believe you. Okay. So this here becomes 0.25p. So we're going to minus that. 0.2p. We're going to minus. Sorry, we're going to add that to both sides, which gives us 1.066 equals 92. So p equals 92 divided by 1.066. what does that answer give us? Oh,
86.3.
yeah, that's right. Okay, so that answer is A. We all good? Emily. Now the people watching the video will have to know that I spoke sternly to you for talking. Okay, question 18. Aircraft typically have a lower factor of safety than structures. Which of the following best explains this? Okay, low risks, better design, higher quality materials, more frequent inspection. Okay, now you could argue that there is better quality materials. I showed you that a screw that goes into a plane can often cost $300, right? Because it needs to have absolute tracking from the moment the screw is forged, cut, the whole way through its life cycle, because we can't risk having a bad screw in a plane, right? Higher quality materials is an acceptable answer. It's just not the best answer. The best answer is very frequent inspections. Yeah, that's the best answer. So I'd be willing to have a student come and argue with me, but I'm going to stand by the best answer is more frequent inspections. Okay, question 19 is another calculation question. So the first thing we need to work out here is we need to figure out what is the ribbon area, right? What is the cross-sectional area that is being cut through? I like to think of it as being like a ribbon. It is that oval shape multiplied by the thickness, right? It would be the cat food tin, so to speak. Okay. So what is the circle component? The circle component is 10 times pi, right? So we're going to call that 31.4. And then there's two sides, right? 10 plus 10, so it's going to be 20. Yeah, so it's going to be 51.4 millimeters is the perimeter of that shape. Yeah? Or it's the perimeter of that shape is 51.4. Multiply that by how thick is the thing? 4? So we're going to get 205, say. Right? My maths could be wrong here, but we're going to call it 205 square millimeters. Okay, now, it says, what is the force required? This question came up later, again. So we said, what is the formula for stress? Stress equals force divided by area, yeah? So if I want to manipulate that formula, so I want to say force equals a sigma. So we're going to have 205 times... What was the 600? So it's going to be the number close to 120, D. D is the answer there. So I did that without a calculator. I mean, look, I have done that question more than once in the last week, but... Okay. This question, I wanted to include a bending question, so I didn't want to... Oh, yeah, I did include a bending question. Okay. Shh. Yes?
Is it still recording? The time in the corner's gone.
Click here to pause. I'm just going to trust that it's recording rather than play around with it. But thank you for letting me know. Usually it stops recording about 15 minutes. If it has, I think I'm just going to live with it. So, okay. If it hasn't, I'm probably unlikely to edit that out. So that'd be an interesting couple of minutes. Okay, excellent pointing out. Okay, so here's our reaction. What are the reactions on either side of this beam? 5, because it's symmetrical. Right? It's symmetrical. So if it's symmetrical, we don't need to spend all that time working out our reactions. I see someone holding their head, which means you just learned something. Yeah? The first thing you should do is you should look to see if these are symmetrical. If they're symmetrical, you don't need to do nearly as much work. Okay. What does the shear force diagram look like? The shear force diagram, it goes, once upon a time there was a beam and there was 5 kilonewtons that went up, and then it went across for 5 meters, and then it went down by 5 kilonewtons. It went along for another 6 kilonewtons, and then it went down by another 5 kilonewtons. Now it was in the negative area. And then it kept going along until it got to the end reaction where it went back up to 0. That is the story of our beam. Yep, our shear force diagram. Okay, our bending moment diagram looks like this. Again, apologies for people who are watching this video in the future. Okay, what is the area of this first block? 5 times 5 is 25 kilonewton meters. Yep. Okay. Now, we now need to know the formula that bending stress, right? This is different to the rule that I tell you is the second most important rule you need to know in the subject. This is like rule 2b. Bending stress equals what? My over I. Okay, so what is the M? We just calculated it. 25 times 10 to the 6. Yeah, because we're going to turn the kilonewtons to newtons and meters to millimeters. Okay, what is the value of Y? Y bar. The distance from the neutral axis to the extreme fibre. How deep is the beam? 300. So half of that distance from the neutral axis to the extreme fibre will be 150. Right? 150 divided by, what is the I? 157 times 10 to the 6. Now those 10 to the 6s, they cross out. And the 150s, I've got 150 on the top, 157 on the bottom. They don't cross out, but they're close enough that we could sort of just take a pot shot at this point and say, it's going to be pretty close to 25. Which of those answers is close to 25? Yeah, so B. So again, I was able to answer that without using a calculator. Okay. So, as we move into the questions, this basically is the same concept. This is where I wanted you to do. This is the only place where you needed to work out reactions in this paper, right? Theoretically, I guess in the previous question 20, you had to work out reactions, but they were symmetrical, so it's pretty easy. Okay, I'm gonna. I could take a photo. What's the chances? We'll take a photo. Okay. Okay. Thank you. Again, this is going to be a pretty boring video for the moment, but we'll see how we go. In the past, what I've done is taken the photo beforehand. That's what I'm really thinking. Okay, so I took this from a past HSC question, and then I modified it a little bit, right? I moved the distances so that way you couldn't just take the answer straight off a past HSC question. Okay, so where would we want to start in terms of taking reactions? Where do we want to go? From about A or from about B? A. Okay, so we're going to do the sum of the moments about A equals 0. I'm sitting clockwise as possible. So I'm going to say 0. 0 equals the reaction at A multiplied by 0, because obviously that's 0 because the distance is 0. Then I've got 12 kilonewtons, which is 1 meter away. Is that going clockwise or anti-clockwise? Clockwise or anti-clockwise? Yeah, so it's plus 12 times 1. Okay, then I have another force, which is 15, and 15 is how far away? 4. Is it clockwise or anti-clockwise? Clockwise, excellent. And then I have minus RB6. Right? So what am I going to get there? We've got 12 plus 60, so that's 72. So we've got 72. 6 RBs equals 72. Therefore, RB equals 12. 1 RB will equal 12 kilonewtons R. Right? Now, if I've got 12 and 15 going down, 12 and 15, that's 27 going down. And if I have 12 going up, how much is missing? What do I need to add for it to balance out? 15, right? I need 15 going up to balance that out. Yeah? So therefore, RA has to equal 15. Pretty easy, all things considered. Now, once we have that diagram, what we're going to have is our story. Once upon a time, there was a beam that at RA went up 15. It went across for 1 meter, when suddenly at 1 meter, it dropped down by 12. It went from 15, lost 12, so it's now at 3. It kept on going for a while until the big bad 15 came along. And the big bad 15, well, that was a different story. The big bad 15, now it was in the negative. How much was the negative? It's now 12 negative. Okay, that's what my shear force diagram. And then the reaction at B brought it back into 0 and all was well. Happy endings. Okay. Now, to draw that diagram, what is the distance of this first block? Yep, 1. And what is the height of the block? 15. So 15 times 1 is 15 kilonewton meters. What about this block? What is the width of that block? 2 meters. What is the height of that block? 12. So it's going to be 12 times 2, which is going to be 24 kilonewton meters. Now, I had some people who had the thing cross the axis. I don't think it crosses the axis. If you think about it, this is positive. All of this range here is positive, and then here is negative. Right? If you think just about in terms of adding up the areas under the curve, we get that value. Okay, that was worth 6 marks. I think almost everyone here got, a lot of people got, this was worth 4 marks if you got the shear force diagram. If you drew something that looked like a shear force diagram, I gave you 1 mark. I may have mentioned that, okay, I'm going to move on. Okay, again, a bad question for exams. Maybe I'll put a photo in, maybe I won't. I did say I'm unlikely to edit this, but who knows. Okay. Determine the nature of the force in members EF and FD. Okay, I'm not going to draw the whole truss because I don't need to. Right? What I draw instead is just part of the truss. Which part of the truss? This part of the truss. Right? That's what I'm drawing. I've got FD, E, right? I'm drawing the left-hand side of the truss. Okay, now I want to find EF. Is that what I'm finding? EF? So to find EF, I have to cut through EF. Now, if you just show me the cutting line, that could get the cutting line alone could be enough to get your mark. Right? Could be lucky. Now, all of these members that I cut through, I'm now going to draw them as being in tension. I'm going to draw them pulling out of the node. And we know when you pull out, it's tension. Okay, so what have I got here? I've got this top one called CD, and I've got FD, and this one here is EF. Okay, I've got 3 unknowns here, right? I've got my target, which is an unknown, and then I have 2 more unknowns. Oopsie. How do I eliminate those 2 unknowns? How do I eliminate CD and FD? Okay, we have names for this. The techniques. Do we use the meetup method or the lone wolf? Meetup. Where are we meeting up? D. Okay, so we're going to say the sum of the moments measured from point D equals 0. 0 equals, well, straight away we've got CD bracket 0 plus FD bracket 0, right? So all we've got left is we're saying this is clockwise, so clockwise relative to D, right? Clockwise, if I put my finger on D, this force of 750, is it going clockwise or anti-clockwise? Clockwise, so it's plus 750. And how far away is that? 1.5 meters. Okay, and then I have my EF. Is that going clockwise? Again, I'm putting my finger on D and turning it. It's going clockwise. So straight away I can tell my sign is wrong, but we can move on from that. We'll worry about that later. Okay, what is the distance here? What is this distance? I'm going to call this distance X. If this is 1.5, okay, the problem is first we need to find the angle. Now, here's what I could suggest. If you just don't have the ability to find the angle, for some reason that part of your brain got lobotomized the day before the exam, I would just make up an angle. I would just say call theta equal 15, right? And just run with that. Make it equal 30 degrees and just run with that. Because then you'll only lose 1 mark. Yeah? Part of the exam is them understanding that you can find angles. They want you to be able to find angles. But you'll only lose 1 mark if you do that. Okay. What we have to instead do is we have to say, well, okay, we know that this triangle has the ratio of 3 times 1.5 versus 1.5, right? Which is the same as a triangle of 3 to 1. Now, if I have a triangle of 3 to 1, what is the angle? Well, I have to do the inverse of tan, or arctan. Inverse of tan, 3 over 1. I know I did this on Emily's paper. Can you tell me what that angle was equal to? Is that 18 degrees? Turn the pages so you can find what. 18 degrees. Okay. Okay, now that we know what the angle is, what we want to do is we want to say if that's 18, okay, what would the short side be if the hypotenuse is 15? So we're using the hypotenuse and the opposite. Hypotenuse and opposite, what are we going to use? Sine. Yeah? So we're going to call this value x equals 1.5 sine 18 degrees, which I think was like 0.47. Is that right? 0.47? I wrote it down on your paper. Okay. So, if we go back to our moments, some of the moments. We've got something that's multiplied by 0, something multiplied by 0. 750 times 1.5. EF multiplied by this distance of x. So what I'm going to write now is, what's 750 times 1.5? Did you have that? $750 times 1.5 equals 1125. Divide all that whole thing divided by 0.47 equals. I got 2393 newtons. Now I think I asked for the answer in kilonewtons. Is that right? Yeah, that's tricky. Tricky. I think I only took 1 mark off for people not writing down things in the right units. Now, the HSC tries to be pretty friendly, right? They're not out to trick you. But do pay attention to it, right? Do pay attention to newtons, right? Do remember to multiply things by gravity. You'll lose marks if you don't, right? So the answer is, I mostly accepted 2.4 kilonewtons. Now, my answer was negative. I made an assumption that it was in tension. My answer was negative, therefore it must be in compression. That's right. Okay. What about FD? Can anyone tell me what deals with FD? Zero force member. How could I tell? Because I had a supplementary angle, right? Straight line angle with no external force, right? Yeah. See how it's a straight line? CDE is a straight line. Yeah. I have FD. Well, it makes a supplementary angle, right? Yeah, like in maths. Yeah. If there's no extra force on there, zero force member. There's a link on videos in the trust section that talks about zero force members. Okay. Only a couple of people, I think, spotted that quickly and easily. A lot of people did a lot of hard work before they gave up and realized it was unsolvable. Now, this was a hard truss, right? For 4 marks, I made the zero force member 1 mark, right? Just so that you didn't get too punished for not getting it. But it is a tough question because whenever we have a truss that meets at a point like this, it can be very hard when people try to use the lone wolf or the meetup method that they don't realize where they need to take their moments from. So I think this is a really good test. If you got this right, you know trusses. If you didn't get it right, well, there's more work to be done. I will say that this truss was one of the ones that is in our set of practice trusses. So if you'd done all the practice work, then you would have got it. Similarly, this question, I took this from practice questions. I just changed the values. Okay, so for 21C, I can see people are in the pack-up mode. We've already done a fair bit of detail already. I will call it here, and we'll go through a little bit less calculation-based stuff next time. Is there anyone who wants to talk to me about anything? Anyone who wants to fight for marks? I need those papers back because I need to check that you've entered in the values correctly.